Okay, so do you hear me? Does it work? Okay, fine. So thank you very much for inviting me here in this very nice place, this conference. And so far today we've been hearing a lot of interesting talks about quantum systems. So my talk is going to be about a classical system, maybe the most classical and the most long range of the interactions, namely classical gravity. And in particular, I'm going to be speaking about in classical gravity of an interesting problem, the so-called radial orbit instability, which happens in stable but radially biased systems. So I will, how does it work? I will, okay. So I will say first a few things that maybe have been said in the past days already about self-consistent system with long-range forces in their continuum limit, and then speak about the radial orbit instability in Newtonian gravity and in modified gravity, and then with long-range forces. After that, I will speak about some numerical results concerning the discreteness effects, the n-body chaos, and the continuum limit of such long-range interacting system. And finally, if I manage to arrive, conclude and summarize. Okay, so as we have learned in these days, no, classical. Okay, so classical n-body systems with interaction decaying as an inverse power of the distance between particles. In this case, I'm speaking about gravity, but it can also be plasmas, where we have the 1/square force, are principally dominated by mean field, by a collective effect. When n it's very, very large, as we have in plasmas, neutral and non-neutral plasmas, or in galaxies or star clusters. So due to the very large number of particles we have in this system, it's natural to speak about continuum limit. Say, we send n to infinity because it's very large, and then the individual mass or charge of each particle, we send it to 0. And then consider their dynamics in terms of phase-based distribution functions, which are, roughly speaking, functions which count how many particles you have in a phase-based volume per interval of energy or conserved quantity. And such systems in this frame are described by the so-called collisionless Boltzmann equation for the phase-based distribution F, or Vlasov equation in the jargon of plasma physics, associated in the simplest case to the Poisson equation, which is here the field equation for the classical gravitational potential associated to the mass density that you can recover as an integral over the velocity space of the phase-based distribution function. And so in this interpretation, so we are considering some sort of fluid in the six-dimensional, in the 6D single particle phase space, rather than the dynamics of particles, without considering any collisional effects. But you can also see this thing as a series of momentum performed over the Liouville equation, rather than taking taking out the collision part out of the Boltzmann equation. To give a few numbers why the collisionless limit it's relevant, let's consider, for instance, a galaxy hosting 10 to the 12 stars. The collisional lifetime of such system, which can be given in terms of typical velocity and mass of the particle and the Coulomb logarithm of the minimum to the maximum impact parameter and average density, exceeds quite a few Hubble times 13 giga-years. So for a galaxy of 10 to the 12 stars, the time that it takes to the system to account for the fact that it's actually made of particles is way larger than the age of the universe. And if we go to completely different systems, so say charged particle beams propagating in linear accelerators, they typically contain up to 10 to the 10 ions or electrons, and they propagate for a few minutes, for a few seconds in linear accelerators. but they have relaxation times computed, collisional relaxation times computed in this in a similar way, which exceed minutes. So again, the order of magnitude between the collisional lifetime and the actual lifetime of this system, it's very different. So it's safe in a way to speak of collisionless system. So now let's speak about the radial orbit instability. What is the radial orbit instability? So suppose you have a self-gravitating spherical system which is stable, and it's a static. It's stable solution of the it's equilibrium solution of the Vlasov-Poisson equations I've been showing before. And suppose it's principally dominated by radial orbits, so namely individual particle orbits with very, very low angular momentum. So these systems are known to be violently stable, even though they, when they are made of particles, are a sampling of an equilibrium phase-based distribution in the frame of the Vlasov-Poisson equations. And typically, from both analytical and numerical studies, it has been found out that when this ratio between the kinetic energy, twice the kinetic energy in radial motion to the kinetic energy in tangential motion exceeds a number which is roughly 1.5, these systems appear to be unstable, leading to a recollapse and to end states after they relax, which are markedly triaxial, as we can observe in real stellar system galaxies. Elliptical galaxies are triaxial. I mean, there's a large plethora of analytical results for the isotropic case, so where you have equally distributed radial and tangential motion in orbits in this equilibrium model. That models with phase-based distribution with a gradient with respect to the energy smaller than 0 correspond to stable system, and this is a so-called Antonov theorem. In a particle-based interpretation of radial orbit instability, it is said that it's triggered by stellar orbits which have a condition with orbital frequencies close to satisfy this condition, where this is the precession frequency that is defined like this, so twice the azimuthal minus the radial system, close to 0. Okay, so when particles have an almost 0 precession frequency, and this is typical for stars with very low angular momentum. So once you put a tiny non-spherical perturbation in the system, once the orbit crosses the perturbation, it has high chance to get scattered back to the perturbation, changing its precession velocity sign, and then accumulating to the perturbation. This thing goes on and on and on in the interpretation of Palmer in the 80s, and interestingly enough, it's not associated to any particular value of the psi of the anisotropy parameter, which I've showed here. Okay, and again, as I was saying, once this non-spherical density perturbation is formed, it will grow more and more and more, and then the end system will be markedly triaxial. Okay, so this, as far as it concerned, it's a well-known story in classical gravity, although there's lots of controversy on it, which I'll come to it later in my talk. But there are also numerical results in modified Newtonian dynamics, which is an alternative theory of classical gravity, which doesn't need the dark matter to explain the dynamics of elliptical and spiral galaxy, which sort of substitutes the Poisson equation with this nonlinear Poisson equation, where this mu is a function of the potential gradient ratio with A0, which is a fundamental constant. It's an acceleration. And again, it's a nonlinear theory, but it's a local theory. So the potential in X is connected to the density in X, and not to the density elsewhere, as in the Laplace in Poisson equation, which is a linear and local equation. And then it has been found out in numerical simulations that modified Newtonian dynamic systems are more stable than single components, so models without dark matter, in Newtonian gravity with the same phase-space positions for particles and their velocity, but vice versa, Mond systems are less stable than their equivalent Newtonian counterparts. So are models with the same phase-space distribution of the Mond system, but additionally a dark matter halo, which accounts for the potential that otherwise would be computed in Mond. So and since okay, it's a nonlinear Mond, it's a nonlinear theory, but it's again long-range theory like classical gravity, and in the strong Mond limit, it behaves sort of 1 over r instead of 1 over r squared with the distance between particles. I mean, roughly speaking. So the 1 over r force is not the modified Newtonian dynamics force, but it's something that asymptotically converges to it either in the very weak field regime or when you are very far away from the source. Okay, so there are number of open points in concerning radial orbit instability, both in modified dynamics and in classical Newtonian dynamics. For instance, what is the depending on the specific force? So is really working in the same way in modified dynamics or in classical gravity, because we just have the simulation results. I mean, there's not much analytical theory done in dynamics concerning radial orbit instability. Or there are some aspects of this radial orbit instability that are specific of the 1 over r Coulomb force that has many interesting properties, such as satisfying the Newton theorems and so on. And in particular, and this would be the main part of my talk, so what is the role of the discreteness effects and internal or external noise in triggering and enhancing the radial orbit instability? Okay, so another thing, so phenomenologically, is the radial orbit instability something that it's because of the long-range nature of the gravitational force, or it's more an amplification of local effects that would also happen in more short-range forces? And in order to tackle this problem, we did something that at first might sound crazy. So instead of studying numerically ρ in radial orbit instability in classical gravity, we studied in general forces with 1 over r to the alpha power law behavior. So here, of course, we don't have, as in the very nice Newtonian dynamics or in Mond, we don't have an analogous of the Poisson equation connecting the potential and the density. So we are forced in all cases to compute either analytically or numerically the potential associated to a given density distribution with the Poisson integral, instead of solving the differential equation as we could do in the linear case in Newtonian gravity, or in the nonlinear case with Mond. Okay, we assumed 2 different density profiles. So one which is flat chord, so the density goes in the center, so it's almost constant in the center and then decreases far away as like this, or a model with actually a strong density peak in the center. So let's call it flat chord and cuspy model. Okay, and then we've been building semi-analytically the phase-based distribution as function, the anisotropic phase-based distribution with a standard Ozypkov-Merit technique, which is nothing more than an Abel inversion of the Vlasov equation and the Poisson integral, as function of these quantity Q, which is basically the sum of the energy per unit mass plus this function of the angular momentum per unit mass. Here, this RA is the so-called anisotropy radius, which has his own definition in astrophysics, but here take it as the radius for which the matter inside, I mean, this radius is it's almost isotropic, and the matter outside is dominated by radial orbits. So we built stable we built stable and unstable, I mean, equilibrium phase-based distribution for the Vlasov equation with this technique, and then we sampled them with particles in order to perform our nice numerical simulations. As you see here, for different values, for the same density profile and different values of the force exponent, so say with smaller alphas, we go to forces that are more long range than gravity, so they pull more and more with respect to classical gravity for fixed normalization, and for alphas larger than 2, they pull less than gravity, so they are in a way more short range. Okay, and this alpha is limited in the open interval 0, 3. Okay, so it's always smaller than the dimension of the system. Okay, because we were talking about the spherical system in 3D. So we have very different, functional forms for different exponents at fixed value of the anisotropy. So there again the ratio between kinetic energy in radial motion and tangential motion. So a few of them are markedly non-monotonic. Notice. Okay. And then after building this semi-analytic equilibrium model, we performed numerical simulations. Everything gets normalized to the dynamical time and to unitary masses and core radii. So here in the left, in the left-hand panel, I present the evolution of the anisotropy ratio, the virial ratio, which is a measure of the collisionless. It's a measure of the distance from the equilibrium of the model. It's the ratio of twice the kinetic energy over the modulus of the virial function. And the axial ratios, so the ratio between the minimum and the maximum semi-axis, as well as the Lagrangian radii containing the 1/10 of the mass, half of the mass, and what was this? 50% of the mass of the system. Okay, for the equilibrium model, and here we say in the equilibrium model, so when this psi, this anisotropy ratio is 1, everything stays constant, there's no evolution. And then for the maximally anisotropic model, so the last one, the last model that you can construct before the phase-based distribution becomes negative in at least 1 point, so therefore the consistency is violated, and the phase-based distribution doesn't describe anymore a real system, because it's not anymore a probability density function guessing as it gets negative values. So here we see that all the maximally anisotropic models that are violently unstable in a matter of a few dynamical times, they start changing their shapes, as we see here from the evolution of the maximal to minimum, minimum to maximal semi-axis, and also from the anisotropy. So they tend to isotropize. The psi, as one would guess, diminishes, while this also diminishes, and the system starts flattening. Then here in the right-hand panel, we have a different thing. So at fixed anisotropy, this is independent of alpha. At fixed anisotropy value for different force exponent, we're plotting the same things as before. And it turns out that for fixed psi, the models with larger values of alpha, so the models with which are more short range than gravity in a way, are more prone to radial orbit instability. They tend more to be influenced by this, by their anisotropy in velocity space, and they become triaxial. And typically, in general, this instability sets in around 15 dynamical times to give an order of magnitude for the time of ignition of the radial orbit instability. All unstable models get their final axial radii and anisotropy values within 2 to 5 dynamical times. So which is, again, another indicator that this is an instability. It's a process that it's very fast compared to the collisional time scale. So in principle, one should say that this is a pure long-range effect, even though it's stronger in the short-range, more short-range case, and in principle, one doesn't have to consider the effect of the discreteness effects of the system. So whether there is an influence of the fact that the system is actually made of particles, because it happens on scales way smaller, way shorter than the collisional time scale. So in general, this is just qualitative observation of the final and relaxed end product of the numerical simulations. We have that larger values of alpha, so more short-range models produce flatter system, while for a given initial anisotropy ratio. And in general, we never find axial ratio, no matter what interaction, what alpha we put here, that are smaller than, larger than 0.7, like in observed elliptical galaxies. So we never have something that is more flattened than this, interestingly enough. But indeed, there are flat system in astrophysics. So, but we don't have anything that it's in between a disk and something which has a 0.7 flattening parameter. So this again discriminates between the formation patterns of the two different astrophysical systems, to say something. So again, it's interesting that we always have monotonic trend for the anisotropy, for the consistency anisotropy radius and consistency anisotropy parameter with alpha. So here it goes from 1 up to 2.5. Here it's 2, which is gravity. It's the value of psi as function of alpha for consistency. And here it's what we find for the anisotropy radius and for the initial value of the anisotropy as function of alpha, which says that models with smaller alpha, so more long-range models, are able to support larger amounts of anisotropy and are in general more stable. So at fixed R, at fixed consistency, at fixed anisotropy radius, they are more anisotropic and therefore more unstable. But it's a bit tricky, but at fixed psi, models with smaller alpha are more stable than models with larger values of alpha for the same density profile, of course. Interestingly, another observation is that there's apparently no effect, maybe at least for models with larger alpha, but only in the tails. There's no effect on the number energy distribution, which is not the distribution function, but it's sort of related to it. It's just basically the number of particles per interval of energy. Where the distribution function is this times the density of state of the system. So this evolves very little, even though the radial orbit instability appear to be very violent, at least looking at the plots I've been showing before of the anisotropy parameter or the axial ratios as function of time in numerical simulations. So there is basically no mixing in energies because the number energy distribution are sort of conserved up to 40 dynamical times. But in configuration space, I mean particle velocities and in orbit space, so eccentricities of the orbits and their inclinations seem to mix very much, because we pass from a spherical system to something that it's triaxial, that does not admit actually closed planar orbits. Okay, so this is the wrap up for the first part of my. So how much time do I have? 1 minute. So this is the wrap up for the first part of the talk. So independently or on alpha, we have that all isotropic models are stable. So stability for models with long-range interaction is not prerogative of the 1/r² force. All marginally consistent models are unstable, and radial orbit instability is stronger in models with high values of alpha for namely for short-range forces. All unstable models develop significant changes in the acceleration, the anisotropy ratios before 15 dynamical times. So it has not much to do with the collisional effects in the system. And okay, so this is what I was saying on the triaxiality. Okay, so let me skip to the other result that I wanted to present. I skipped all of this about discreteness effects. Let me show you this final plot. So this is the maximum Lyapunov exponent as a function of n for 3 different anisotropy parameters and 3 different density profile. And here you say that contrary to what was supposed back in the days, in the early 90s, the radial orbit instability is not associated to the global degree of chaos of the n-body problems, so say the largest Lyapunov exponent in a way, but because there's basically no difference between the values at fixed n and at fixed density profile between the maximum Lyapunov exponents. So they are basically all the same for different values of the initial anisotropy parameter and for stable and unstable system. But here, looking at some proxy of the Lyapunov spectra of the systems, we have that more anisotropic models have a larger fraction of the Lyapunov spectra with larger values of lambda, but comparable maximum Lyapunov exponents. So with this, I would like to conclude everything, and thank you for the attention. Questions, if any? Thanks.